And we will start with Walter Roest, CNEXO and Ifremer, over 50 years of worldwide marine scientific research and exploration of the French easy.
Celui-là, il est plus puissant. Et les slides, tu peux les passer avec ça directement.
Thank you very much. Ladies and gentlemen, it's a great honor for me to present today a little bit of the exploration history of CNEXO and Ifremer. And I would like to specifically thank the organizers for organizing this symposium at the occasion of the anniversary of the landmark paper by Le Pichon. I would like to start with a quote. I don't know the date of this quote. I've read it several times in different occasions, where he stated that when he started his research career in '59, the mid-ocean ridges were really not known. The fact that the largest structure on the planet, 60,000 kilometers, existed was not known. And it was really the exploration of the oceans that led to the quantitative model that we now have and that can actually predict a certain number of parameters. And this model was really based on oceanic data. So one of my messages is today that acquiring data of quality in the oceans is still actually relevant today. And I think we need to continue that effort. I'm also very pleased to see a magnetic map, actually, because I've spent a lot of my time working and processing and acquiring magnetic data in the oceans. And this map really reflects very well what is now very obvious as being isochrones of equal age that are symmetric across the ocean ridges. So I'll talk a little bit about the early days as an outsider, of course. I will talk about the plate tectonic theory from the global scale and some in situ observations. The science and technology today performed by Ifremer. I want to end with a few words on law of the sea and continental shelf. So the paper by Le Pichon was published in Journal of Geophysical Research, and it's true it was written when he was at Le Monde, but as he recalled this morning, he actually was already at CNEXO in Paris when the paper was published. And in fact, it's true that Xavier Le Pichon has had a very important influence on the scientific work that was done at Ifremer. First, he was there as director of the scientific department, but even after he left, he was head of the scientific committee at Ifremer, and so he had a very big influence on the direction that actually was taken, and particularly the importance of pluridisciplinary research. So CNEXO, for those who don't know, was actually created in 1967, and it's a public institute of industrial and commercial character, which is a very specific French construction. It was actually created to develop the knowledge of the oceans and to do research studies aiming at exploiting, so that's very explicit, resources contained on the surface of the ocean, in the mass of the ocean, their soil and their subsoil. And the biggest center of CNEXO at the time, of which we have seen pictures at the very beginning, was the Centre Océanologique de Bretagne, close to Brest. At that time, the main vessel that was used actually for ocean exploration was the Jean Charcot. And just to finish the brief history, in '84, CNEXO was actually followed up by Ifremer, which was a merger of CNEXO and the Fisheries Institute. And it was actually, again, created to promote fundamental and applied research, expertise, and technology. And in the name of Ifremer, we still have exploitation of the sea. The main issues were understand and evaluate the resources, improve methods of monitoring and forecasting, protection and enhancement of the marine and coastal environment, and to promote socio-economic development of the maritime world. On top of that, Ifremer is managing now, as of today, the complete oceanographic fleet in France for the benefit of the scientific community. Just as a note, I would want to say that within Ifremer, the human resources represented by the marine geosciences is only around 6%. So Ifremer is about 1,500 people in total today. So this is a map that shows the marine geoscience tracks actually conducted by Ifremer and CNEXO vessels over the history of the last 50 years or so. And we can see that although the vessels went everywhere in the world's oceans, there is nevertheless quite a bit of concentration on the areas that are the French exclusive economic zone. And there were specific programs related to those. For instance, ZEE Gascogne, which is the Bay of Biscay, work done offshore French Guiana and the Antilles, or in French Polynesia, in the southern Indian Ocean, and around New Caledonia. But before actually going a little bit further on that, and we've already heard a lot of this morning, so maybe there's some repetition, I would like to point out those 5 papers that were published in 1965, 1966. And the main reason why I want to point them out is because it's actually the data that is important. Some of the conclusions that were reached were actually likely not correct or only partial. The first conclusion, for instance, on the seismic refraction measurements was actually very prudent, and it said those measurements should be taken into account in any theory on the formation of mid-ocean ridges, which is, of course, good. However, when it became to modeling gravity and seismic refraction data, what was found clearly the observation that, unlike the prediction for isostatic compensation, there was no actually thick crust underneath the mid-ocean ridge. So there was actually an anomalous mantle, and the conclusion was that this mantle needed to continue below the flanks of the ridge, underneath the normal mantle that was observed there. Magnetic anomalies, of course, they were observed, but they were mainly related to the high heat flow belt, so something in relation to the Curie temperature. And as far as sediment distribution, the conclusion was that there was no reason to believe that significant continental drift had occurred during the Cenozoic. And a similar conclusion from heat flow. Of course, we know that things happened extremely fast. We heard that this morning. In only a few years, or maybe a matter of less than a month, maybe, or several months, these data were actually used and put into a context that were able to be understood correctly. And that was this model with the 30 spreading rate determinations, 60 azimuths from fracture zones, and 6 rigid plates, which we've seen this morning. So what is the importance of that? We have a coherent quantitative model. The tectonic plates include the continents and the oceans, and what we can do with that model is we can make predictions. And in the paper, Le Pichon mentioned that one of the most important conclusions is likely that he was able to constrain the velocity of convergence in trenches, which was not possible before. But those predictions go largely beyond geology. They can cover topics like hazards, paleocirculation, paleoclimate, marine biology, natural resources. And I think we will hear some of those applications over the coming days. So at that time, the fleet of Ifremer, which originally had only 2 vessels, Thalassa and Charcot, was expanded, and ships were positioned in the Pacific Ocean, in the Atlantic Ocean, and also a vessel was built to actually support manned submersibles. So I'd like to insist one more time on the fact that it is important to collect data. And so Le Pichon went out to sea, and as usual, most of the time it was not easy work, and it still is not easy work at sea. There's always things breaking down, and in his report, which he wrote in 1970 from the Jean Charcot, he pointed out that the buoy test was disastrous, the air gun was leaking, didn't work only 3 hours, the magnetometer broke several times, but he also pointed out that the results of the refraction were far superior as the ones obtained by Lamont. A little bit later, and he mentioned this offshore the Hellenian Ark on the Nadir in 1979. I want to spend a few words on famous because we go from a plate tectonic model which covers the entire planet to the idea 2 years after we've put man on the moon that we should actually go and look at the axis of the mid-ocean ridge by a manned submersible. And this was not easy because there was quite a bit of resistance, particularly on the American side. people felt that submarines had never contributed anything to science, and there was no use to go and try and observe a mid-Atlantic ridge with a manned submersible. But nevertheless, I imagine with a lot of persistence, the activities were started in 1973, and the famous project, the French-American Mid-Ocean Undersea Study, started at that time with a detailed investigation of the mid-Atlantic ridge between 36 and 37 degrees north. And so here we see Le Pichon with the director of the Oceanological Center in Brest in front of the seafloor map. And one of the things they wanted to do is to search for hydrothermal vents. So here are some pictures from that time. There was Archimede and Sayana. They completed 27 dives, Alvin 17 dives. More than 100,000 photos were collected, 1,500 kilos of rock samples. They found actually hydrothermal deposits, but they did not find any hydrothermal vents active. It was only about 2 years later that those were discovered off Galapagos. So if we think back a little bit about what was known of the ocean floor, this is an artist's impression of the 1968 map by Heesen and Tarp, painted for National Geographic magazine. That was in 1968. And we had to wait till about 83 to get the first satellite altimetry-derived map. And we can see that this map is remarkably accurate in its overall depiction of the seafloor, but of course in the details, for instance, the trend of the large offset of the Charlie Gibbs fracture zone is clearly not in the right place. So in 1992, we would be very proud to actually already produce kind of a 3D diagram of this kind of quality based on multi-beam data collected by the Atlantic research vessel on the 1520 fracture zone. And for instance, one of the important observations made at that time was that there was mantle rocks outcropping at the seafloor, and there was release of methane that could be detected above the seafloor. And this was, of course, a reflection of active processes. So today, when we actually compile multi-beam gravity bathymetry data, this is an example of the Cook fracture zone, which offsets the Three Kings Ridge and the Loyalty Ridge between New Caledonia and New Zealand. Or this map, which was already shown today, which I find a fabulous map, compilation of the Mediterranean Sea based on multi-beam bathymetry data, and some of that are very high quality data, and completed with background satellite-derived bathymetry data. So in terms of the plate kinematics, there were more and more details available based on the mapping, based on the gravity data. And this is an example of a study done at the time by Oliver in '84, showing the history of the seafloor spreading in the central North Atlantic Ocean. And on this map, he indicated in this brown color areas that were of significant anomalous topography, and in the green colors areas that he considered were deformed and likely related to either early deformation or hotspot activity, or maybe plate boundaries that had existed at the time. This is another view of that same model, but now taking Africa as fixed, and we see how actually the different land masses around Africa move away from the blue towards the red, and then subsequently white color in the present day configuration. I wanted to show this map because this is a rendition of a paper we wrote with Dietmar Müller in 2008, which actually combines all those generally regional models for different ocean basins from different sources, and actually shows the age of the ocean floor, the ocean lithosphere in color. It also shows the present knowledge of where actually the major plate boundaries are. And of course, this model, which has embedded in it a self-consistent plate tectonic model, can be used to make predictions, to make reconstructions in the past. And I think Dietmar will tomorrow talk about, for instance, the carbon cycle, how we can study that in the past using this self-consistent model, which obviously is wrong, but nevertheless, it can be used for such kind of purpose. If we compare that back to the original map of this 68 paper, and compare that, for instance, to what everybody can see today in Google Maps, it's actually not at all very wrong. We see that most of the plate boundaries are in the right spot. Of course, there was only 6 plates. Today we have likely 12 or 12 major plates in any case. But again, the observations made at the basis of it, they remain valid, and that's what is a very important message. So today in marine geosciences, this is our current strategic plan, understanding the geological evolution of the planet, the mechanisms of formation of the continental margins and the sedimentary transfer from the landmass to the deep ocean basins in relation to climate and tectonics, exploration of the geochemical cycles, and also search for minerals, because in the end we are still an industrial and commercial institute, the study of marine geological hazards, and the participation in technological developments necessary for that research. This is our latest research vessel, the Pourquoi Pas, and here we have the Nautile, manned submersible, the ROV, Victor, which can go to 6,000 meters, and this is Bob, which is a bubble detector, which we use to look at active venting on the seafloor, for instance, has been used in the Sea of Marmara to study the fault zones there. Of course, we have a certain number of technical capabilities. I just wanted to point out 2 things that are relatively recent activity, although it has been ongoing, but I think lately it has been renewed, which is the search for minerals, of course, partly because of the lack of, or the scarcity of some of the resources in minerals on land, also the search for rare earth elements. This map shows in red the hydrothermal sulfide permits that actually have been given out by the International Seabed Authority to states to actually explore for those sulfides and try to better understand their formation. So in the Atlantic Ocean, we have Russia, France, and in the Indian Ocean, we have China, Germany, India. So there's a handful of countries that are actually putting in quite big efforts, mineral resources in the ocean. In France, we had, and we may revive soon, a project actually of exploration of the EEZ of Wallis and Futuna, which is on the northern edge, north of this North Fiji Basin, here in this area. And these yellow stars show some of the hydrothermal vent systems that we have discovered in that region. And today, those are mapped actually by AUV. So we can actually not only map the topography of the sea floor, but we can also map the water column. And here we see an inactive chimney. And here we can see an active sulfide mine with a hydrothermal plume in the water column. So this is one of the AUVs. And this is just an example of a black smoker being investigated by the ROV Victor. Last bit, just a few words about the continental shelf. This is actually related to the United Nations Convention on the Law of the Sea. Article 76 allows states to actually claim part of the continental margin beyond 200 nautical miles of the exclusive economic zone if they can demonstrate natural prolongation. And this has spurred quite a bit of activity of coastal states to actually collect data on continental shelves and into the deep ocean floor. Very briefly, I'll show you that the Article 76 of the United Nations Convention on the Law of the Sea actually, on this kind of cross-section where we have continental shelf, slope, rise, and abyssal plain, puts some legal terms which are, first of all, the territorial sea, then the contiguous zone, then the exclusive economic zone, which goes to 200 nautical miles from the coast, And finally, the continental shelf beyond 200 nautical miles, which has to be demonstrated with geophysical and geological data to be a natural prolongation from the landmass. And then the international seabed area, which is actually where the International Seabed Authority manages the search for mineral resources. And the high seas actually start from 200 nautical miles. So just some numbers, what that represent. Here we have a map of the world. In dark blue is the 200-mile zone around the continents. That represents about a quarter of the surface of the ocean under jurisdiction of coastal states, about 120 million square kilometers. We think that there will be about 25 million square kilometers more claimed by coastal states as extended continental shelf. And there's about 70 states that are having entitlement to do that, including France, which already has one of the largest EEZs in the world and still hopes to expand some of its right over the seafloor. And there's more than 80 actually submissions already lodged with the UN. So I'll conclude, just in time I think. I believe that plate tectonics is not yet over. I think it still provides the fundamental tools for understanding the Earth system and for reconstructing back in the past difficult questions related to climate, related to ocean circulation, etc., etc. Also, I'd like to insist on the fact that only a small percentage of the ocean floor is mapped to modern standards, and although satellite imagery gives a very good regional scale picture, it's not sufficient to actually do detailed tectonic studies. So we need to continue that work. And finally, I mentioned that there is significant activities deployed today by many states in the oceans in relation to the law of the sea and the search for minerals. Thank you.